know everything I'm going to say today. So our goal is to be able to learn and explain how the size of ions compares to the size of their parent atoms. Our next goal would be to talk about ionization energy and then kind of its partner in crime, which is electron affinity. On here, this one is extremely important. This one is sort of important, and this one is almost not important at all. Okay? Yes, sir?
I guess I texted you last night about the disclosure. I guess I got confused. Was it like the new
No.
disclosure, or is that just
Nope.
I didn't look at the
There's no new addition to the disclosure at all.
So we don't have to do the thing about the temperature.
No,
We can just keep
you don't. No,
Still applies stuff.
if you saw on the first slide, it said if you want to do retakes, you would have to do those things, right? Yeah, whatever. I don't want to go that far. Yes, Reese. So no, there was no addition to. The blue sheet is not due.
Thank goodness, because I haven't done it.
So, and I clearly was not very clear. If you, like I would do it if I were you, I'm not going to grade it. And then if anyone wants to retest, then they have to for sure turn it in before I'll let them do it. So we'll probably sort of do that. Once we get to chapter 10, things get really, really important that we understand them. And so I'll have probably more assignments there. And it's not that this isn't going to be on the test. This will absolutely be on the test. But chapter 10, 13, 14, 15, 16, 17, 19, 20, they're all really important. So anyway, here we go. Let's just jump right into this. This is not real hard stuff. So yesterday, just in review, we talked about Zeph increasing as we move from left to right. That's because we added protons, but the shielding electrons stayed the same. Then I have this just grayed out sort of subtle arrow. Zeph doesn't technically change up and down, but you do need to know, like the number of it, but you do absolutely need to know that fluorine would have a much higher real true attraction to its outermost electrons than like AT would. And that's because it's really small. And if we're talking about force and we're talking about the attraction between a positive and a negative, you'll remember from last week, we had Coulomb's law. It said force was equal to Q1, Q2 over R squared or D squared. So if they're small, this is small and the force is large. All right, now the value, when we calculate Zeph, we're just basically finding a number to compare, but it does matter up and down. I mean, it's the same value, but definitely the higher you are, the higher the Zeph, even though fluorine and AT would still have a Zeph of 7. Fluorine would have a true actual one much greater. Okay, then the application of this says the size of atoms we have big and we have small. And whoops, there's 2 L's in small. It's not a coincidence that these and these are exact opposites. The larger the Zeph, the smaller the atom. The less the Zeph, the bigger the atom. Okay, so that's a review from yesterday. And then let's jump in here. All right, sizes of ions. Ionic size depends upon the nuclear charge, that's the Zeph, the number of electrons, because they're going to push each other away, and then the orbitals in which electrons reside. These are the 3 things that kind of lead us to come up with this idea of the size of ions. Now, you need to be able to explain, well, state and explain the difference between the size of a cation and its parent and an anion and its parent. And then you need to know why. So that's what the next few slides will be. This is a picture from the book. As you read, it's really good to see this picture and kind of look up and understand what's going on. So you'll notice in this picture, the cation is written on the left of the parent, but the anion is written to the right of the parent. So it's important you see that they switch that, which it does make sense why, but whatever. If you look at it, make sure you notice that. Yep, that's pretty much it. And we're going to talk about why coming up. Okay, so cations are smaller than their parent atoms. You must know that. Clearly, Soraya is more interesting than I am. I mean, I think the slide's great, but apparently people would rather look at her. It's rude. All right, here we go. So, that was nice, but not to me. I'm just kidding.
I'm sorry, your slides aren't as pretty as Soraya. If you want, I'll take it back.
Okay, it's about time. Just kidding. I need more caffeine. Give me a timeout. You look at that slide. All right.
Under the desk.
I don't know what's going on.
Too much. Too much is going on.
Too much. Okay. So here we go. This is the statement. This piece is the why. Okay, so cations are smaller than their parent atoms because the outermost electron is removed and repulsions are reduced. So for instance, let's think of lithium. Lithium is 1s2, 2s1, or here's my nucleus. It has its first s cloud and its second s cloud. You okay with that? But Li plus, we would remove one of these and now it'd be 1s2. So this picture, we would just get rid of this. It completely dropped its outermost level. So this is clearly much smaller. All right. So why? The outermost electron is removed. That empties out the outer shell, and the number of electrons to push each other apart is reduced.
So does family 4 have like the greatest change then, like between sizes?
Well, the problem with family 4, like theoretically, yes, but it can go either way. So you'll notice it's just completely cut out of this chart because it can gain or lose. Family 5, they can, but yeah, I'm not surprised. They're not super reactive. That's why, like when we breathe, most of what we breathe is nitrogen, and we just breathe it in and right back out because it's non-reactive. It doesn't do anything for or against us. All right. Now, the way the question here, yes, Judah.
You get rid of one of the cows because it's adding a proton and the proton and electron cancel each other out.
Say that louder.
So you're getting rid of an electron because you're adding a proton?
No. We're not messing with the nucleus. We have an atom that has an electron right here. We put it by something that will take it, like chlorine. It removes that electron. It still stays lithium. The proton stays the same, but the electron literally moves from the metal to the non-metal. Once it loses, it becomes a positive lithium ion. And it becomes smaller than it was before. Okay.
Yeah, so it loses it and it becomes smaller. I don't know, I've never
It's all right. It's like a house. We cut off the top story. It's gonna be a lot smaller. Yeah, well, okay. The analogy doesn't make sense everywhere.
Just taking the second story, moving it, and putting it right on top of those.
Yeah, there you go. Okay, next, anions are larger than their parent atoms. And this is just simply because electron repulsion. So if you add another electron, there are more of them to push each other away. So we got to remember, like charges repel each other. So the more and more you get, the more space you need. It's like when I got married, we had a Toyota Corolla and it fit the two of us fine. Then we had Derek and we could still live in the Corolla. It was fine. It wasn't great. So we upgraded to an Isuzu Rodeo. And then we had Dallin and it was still fine. We could put four of us comfortably in the Rodeo. But then we had Jace and all heck broke loose. We had to just sacrifice the man card, sell the SUV and buy the minivan. I just needed more space. And now I have Carly and now we fit a minivan very comfortably. If I had another one, it would be time to buy the 15 passenger van and give each kid their own row. You know, like the more kids, the more space you need. More electrons that you have, the more space they're going to occupy. It's not bad. Yep, exactly.
Analogies.
Mm-hmm.
This is what everything's an analogy that might work.
Okay, this is how the test looks, and kids screw it up. It says oxide is larger than oxygen. Why? So the reason why this one's harder for metals, that came fast. If I'm talking about a cation, when I talk about the metal, they have the same name. So like I can say potassium and the potassium ion. And then you would know potassium is probably the element and potassium ion is probably the element because it says it. In this language, you have to remember when we make an anion, we end it with IDE. So oxide, that's your ion. Oxygen is your element. Okay, and I don't think that's hard, but kids get it wrong because they describe it exactly backwards. So oxide is larger because it has two more electrons than oxygen, which increases electron repulsion. Okay. On the test, I have typically, I'll have to change it because I mean, you guys got every test question except for the multiple choice in your group me. It says fluoride versus fluorine. And almost everyone screws this one up because you're used to the word fluoride. You're like, oh, that's the element. This must be the ion. But no, fluoride is in your toothpaste. It is the ion of fluorine. If fluorine was in your toothpaste, you would die. Like hands down. It would hurt really bad. What's that? Yep, this is bigger.
Wait, so IDE is always an anion, or
Yep.
is it just an ion?
It's an anion.
Doesn't I always mean like plus?
No,
No, minus 2.
no. I just means it's an anion. It's a nonmetal that's lost an electron.
So on this test, we have to write out instead of E minus repulsion, electron repulsion.
That doesn't matter.
Are we doing it on the computer, I guess?
No. Unless we get closed down in 3 days.
Do you know how many cases
No.
there are?
I don't. I know that every athlete that tested today was negative. So that's a real positive. Whoa, wait a minute. That's like driver's ed. people are like, left turn up here, right? And I say, right. And they're like, so right? I'm like, no, left. Okay, right. Right? So we use the word correct in driver's ed, not right. All right. Thumbs up if you're okay with explaining sizes of ions.
Wait, but so actually in 3 days there's a chance?
No, 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 no.
Oh, okay.
No, I don't think so.
Whatever days it says I think it is gospel.
No, that's,
There's a chance we might get online again.
I think we have a 100% chance of being quarantined again, but not in the next 3 days.
Hey, you never know.
I never know.
You called my quarantine.
I could get quarantined and then I can just spread it to everyone.
Well, I knew in advance,
Yeah. You did your teacher tracing.
but a lot of them never did. They never traced half the other one. Yeah, we should have had 3 total kids. Okay. Ions, this is not any different than what we learned yesterday. Ions increase in size as you go down a column because N is increasing. So that's just the same as the atom. So you would really never be asked this part. Are we clear on that? Okay, so this is 2p. Oh my God.
David, I think it's time for you to drop this stuff.
Oh golly. This is 2p. This is 3p. What's n representing? The row number. 2, 3, 4p, 5p. So as we increase n, they get bigger, just like the atoms did. Cooper Lloyd.
So that's just all about the orbitals then, when there's more orbitals.
Yep. Okay. This is an interesting thing. I have seen it on the AP test once before. It's not on my test, but just so you know, in an isoelectronic series, ions have the same number of electrons. Iso means same, electronic means electrons. Ionic size decreases with an increasing nuclear charge. So write it down and we'll talk about it for a second. Okay. The first thing you should know is that not all of these are directly compared. This is 2 comparisons that just happen to be next to each other. Okay, because F minus has 10 electrons, Li plus has 2. So we're not comparing the blue and the pinks. We're just comparing these 3 pinks to each other and then these 2 blues to each other. So what we're saying is Li plus, Be plus 2, and B plus 3, they all have just the 1s. Oh my heavens. Oh yeah, it is a 2, sorry. All right, so they all have the same number of electrons, but we'd say boron is smaller, just like we would have with the atoms, because boron has a greater effective nuclear charge. Whether it's an ion or not, it doesn't matter, as long as they have the same number of electrons. It just follows the same idea. So here, both of these have 10 electrons. All right, they have the 1s2, 2s2, 2p6. Both of them match exactly, but fluoride is slightly smaller because fluorine has a higher effective nuclear charge than oxygen does. It has an effective nuclear charge of 7 versus 6. So if they ever compare them isoelectronically, or 2 ions with the same total number of electrons, just the one with the higher Zeph is the smaller atom. All right. So here is our summary. Everything from here up is what we did yesterday. So these are the 2 that we've added right here to our big list of summary. somehow we've caught up. Before the break, we were behind. And then I gave this test on the 10th last year of December. I don't know.
Oh, wow.
I don't know what I did.
We are so fast.
No, not you.
Did we
So,
I know we did it.
yeah, I want to say we, but it wasn't us. But like,
We skipped. Well, I know we skipped the 2-day lab, which we will do. Oh, my wife says she loves me. Okay, sorry, that was not necessary distraction. But I don't remember where the other ones came from. Well, actually, no, I don't know.
So we're all caught up.
In which chapter? Oh, that's true. There is a whole day of quantum mechanics that I did not teach. So that would be 3 days. So I'll probably give you this in a couple days. This test is not hard. It's not one you need a week to prepare. So don't panic when it's like Thursday or Friday. Okay, are we good with this? Okay, then honestly, 80% of what we're going to test is already up here. So we're doing all right. Well, maybe 70. Okay, the next thing is ionization energy, which is honestly one of the most important parts of this chapter, but it follows everything we've been doing. So it's nothing all that complicated. Are you already done? I'm sure that you did. All right, let me give you another job then. All right, so look at that real quick while I talk to my very fast TA. Those look beautiful. All right. Whew. Ionization energy is the energy required to remove an electron from a ground state of a gaseous atom or ion. Now, I mean, we don't usually have like gaseous iron in this lab, but
That sounds good.
what?
Yeah, that sounds very bad.
Gaseous iron?
Yeah.
It would
you have to get it.
like 4,000 something degrees. Yeah.
That's how big you get.
Yeah, it'd be like vaping on the sun. Okay. Okay, well, blah, 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 who cares? That's how they measure it. But we can still talk about it at room temperature because once again, it's one we're going to use to just compare two things to another. All right. It's important that you understand what first and second ionization energy means. And 99% of the time we talk about ionization, we're talking about the first ionization, but occasionally we talk second. First ionization energy is the energy required to remove the first electron. Weird. So we'll use lithium again. Lithium has 3 electrons. Its configuration is 1s2, 2s1. So IE1, or the first ionization energy, would be the energy required to remove this. If I had my boxes, all right, I'd have one here, and one there. So the ionization energy 1 would be the energy required to remove that. And it'd be like 300, I don't know. It's on a slide here in a minute. IE2, we would now be trying to remove a core electron, and it would be like a ton higher. Okay, so the second ionization energy is the energy required to remove the second electron, and we could have third, fourth, fifth, sixth.
Pretty much what we already kind of talked about
Yeah.
the atom
It's
falling back down and needing more energy as opposed
the electron. Yeah, it's definitely all related to everything we've done before. Okay, here is our table. Lithium's not even on here. Oh well, it doesn't matter.
Wait, so the second one you would remove would be harder to remove?
The second one is always harder to remove because you're removing one from a more positive thing. We'll go over that. It's coming up. It's right here. It requires more energy to remove each successive electron. Now, there are exceptions we'll talk about in a minute. The reason why, all right, is because so we have sodium, I take away one electron and it now becomes Na plus. You okay with that? The next time I remove an electron, I'm now trying to remove a negative from something that is now more positive. Okay, and then I have Na plus 2, and now it's even more positive, and I'm trying to remove an electron. So it always takes more to remove the second because you're removing one from a more positive atom, well, ion, sorry. Okay, this is really important. This is almost always on the AP test somewhere. When all valence electrons have been removed, the ionization energy takes a quantum leap. That's what the book uses. It has nothing to do with quantum. It just means it takes a large leap in energy. And you can see that represented here. Much more energy is required to remove a core electron than a valence electron. You must know that. All atoms hold on to their core electrons tightly. Some atoms do not hold on to their valence electrons very tight. Those would be metals. Okay, so you can see this illustrated right here. Ionization energy 1 for Na is 495. For 2 is 4,562. It's like a 10 times greater amount of energy to remove the core. But magnesium, it's 738, and then it's 1451. And that's okay. That's not a huge leap because Mg's in family 2. I can remove 2 now before I get to a core. But once I get this number, it's gigantic. Now, the AP test almost always asks this in the following way. It will say the following ionization energies represent element X. Okay? And it'll be a table like this. So those, it shouldn't be IE, I'm sorry. So it'd be like, I don't know, 500, 5,000, 5,865. And then, so you'll have this data, and then it would say, what ratio would you expect element, oh my, whatever, that says expect element to form with oxygen. This is 99% of the time, even higher than that, how this question. What's that? The answer is 2 to 1. Garrett, will you explain how you got that answer?
Well, it obviously has one valence electron.
How? Don't act like everyone in here has no idea what you're saying.
Because from I1 to I2 is a big leap, right?
Okay.
Big leap. So quantum. So quantum. Yeah. You know that there's only one valence electron, right?
Right.
And then oxygen, it's missing 2 valence electrons. You know that, like H2O, 2 H's to 1 O. So you can just figure 2 to 1.
Okay.
Oh, because you're saying that it's hydrogen. It's like it'd be like
It's something from family 1.
yeah, basically.
Wait, so if you have like magnesium and then
It wouldn't be magnesium. Magnesium has 2. It would
Well,
have because it only has one valence electron,
if you have
which is going to make a
phosphorus
+1,
and then
which would be
gold
family
or
1.
something
Right.
like that.
And then how do you find the ratio to the oxygen?
By the drop and swap. You should know oxygen by now. You should know it's -2. This will be a +1. So we need 2 +1s to every 1, -2. So this is the answer. This question, I've seen it on pretty much every single question or test. It's in the multiple choice.
So it's
all,
just a
it's all
drop
about
and
where you
drop.
can see the big jump.
Yeah.
Broski, that means I'll get at least one question right. Look at me go.
Well, so if you look at
Yes, Judah. Yeah. Because quantum really in science is a thing. So it's also a term for big or large, which is funny because it really means something super small. I just need to delete it out of the notes because it's dumb. Like it's not bad English, it's just dumb.
how come it can be, oh, just because the way the question is asked is that how many, okay, how come it can be 1 to 2, but it has to be 2 to 1? Like, what ratio do you I don't know.
Yeah, could you do like
Who's okay? So here's the same question, same stem, so I don't have to rewrite it. If it was 500, 1120, and 4,000. Since this is your big jump, that means it's something from family 2, because 2 of them were easy to remove. The third one was not easy to remove, like relatively to each other. So that means it's from family 2, which means it forms +2 ions. And if it were to form with oxygen, oxygen forms -2 ions. And the charges, if they equal 0, then it's a 1-to-1 ratio.
and you don't even need to know what like
You don't need to know what element X is. You just know it's from family 2.
so what if it's like a -2 or something? Is that just like would that look different?
Yeah, it would look different. You'd have a lot bigger table. And then it would say, what would its ratio be with sodium or a metal? I've never seen it that way because then the table's got to go like all the way over and they're just too lazy.
Yeah.
It's almost always this exact question.
Wait. So how did you figure out the other one was so the other one was family 1 or was it?
The first one was family 1.
Okay.
All right. I don't know how that went, but okay, trends in first ionization energies. These are super, super important. You can look at the table and get it good enough pretty much. Down here, they're really low. And up here, they're really high because it's so small. And it's in family 1, but a lot of times it fits better right here. Because ionization energy, like we're removing it from this tiny atom that is a lot more like fluorine than it is like these big fat metals. So hydrogen's a weirdo, so is helium, because helium, a lot of times it's easier to put it here on the periodic table and talk about it. Okay, so we've seen something already that follows this same pattern in this chapter. What does this trend mirror? All right. Okay, it's inverse of size. It's directly related to something else though. Zeph. Okay, so make sure you understand both. If you have a high Zeph, then you're going to have a high ionization energy. So all these have a high Zeph. All these are noble gases. They're the highest of all. That's why they're noble gases. Look at how much energy it requires to remove an electron from these. Okay, these don't react because we're going to learn that we're going to have a balance between the ionization energy and the electron affinity, which is coming up next. And the electron affinity of a noble gas cannot overcome the ionization energy, so they don't react. All right. So as one goes down a column, less energy is required to remove the first electrons. For atoms in the same group, Zeph, this is the Y. For atoms in the same group, Zeph is essentially the same, but the valence electrons are farther from the nucleus. The farther something is away from the nucleus, the easier it is to remove it from the nucleus. Okay. Generally, you gotta love in chemistry when we use the word generally. That means red alert. We got something wrong going on. Generally, as one goes across a row, it gets harder to remove an electron. Generally. The reasons why, like the discontinuities, we'll see in a minute, they make sense. So don't panic on them. All right, and that's because as you go from left to right, Zeph increases. The last two slides are really important. Now, here is a picture of that. This is a graph illustrating the first ionization energies for each row. And then we'll talk about these dips here in a second. I think they're like in 2 or 3 slides, but whatever. They sort of make sense. Okay, are we all right with the slide? Okay. Oh. Okay. So here would be a question you should be able to answer. Why do metals have low ionization energies? Will you talk to your lab partner about that real quick?
They have a low Zeph, which means that theirs are going to be more spread out, and then so it's easier for them to be taken away. It's how much energy it takes to take it away. So if they're more spread out, it takes less energy to just nab them. Yeah, the less like it's like grip. So like the ones that have more Zeph have a stronger grip, and the ones that are more to the left have a weaker grip. So it's like, so they're like goes from this for metals to just, and then or like this when you're really taking it apart.
All right. So here's my answer typed out. Because they have low effective nuclear charges, which is Zeph, which makes the outermost electrons less attracted to the nucleus and therefore easier to remove. There's a lot of words there, but it's pretty much what I heard the 4 people around me say.
Did I do it right?
Yeah. All right. Are we comfortable with that? What? Oh, no. I'm going to take that out of your pay. The broken glass thing's right behind you. Nope. Behind the door, metal can. No, I don't pay her. It was a joke. No, it's fine. I break them all the time. Did you hit it against the side of the? Yeah. Most of the time I break one, I'm like swirling it to get crap out, and I just hit the wall. I'm like, oh my. Yeah, it's okay. I literally have 100 years of glassware in this room, so I'm not worried about it. Thank you. All right, here we go. All right, there are, however, 2 apparent discontinuities in this trend. I did not know what this word meant until I taught this class. Yeah, hey, sorry, okay. I didn't study words when I was a kid. Okay, so it's these dips. The first occurs between group 2 and 3, or family 2 and 3. And that the reason is because the electron removed from the p orbital rather than the s orbital. That means the electron is farther from the nucleus, and there's also a small amount of repulsion by s electrons. Okay, now you're going to write, but please listen to what this is saying. It is saying it requires less energy to remove this one than it would one of these. No, this is a 2s and a 2p. So if it was a 1s, then we'd be there. All right, so since we have a p orbital, it's a little bit farther away. It's being a little bit pushed away by these. It's easier to remove than one of those in the s. Yeah.
So how does like carbon, so then how do they like stay on 4 times? Is there like only 1 in the S?
We're gonna, yeah. It's called electron promotion. And family 4,
It's like buffered.
like what?
Like buffered.
But it doesn't always be that way. You have to, at the start of the reaction, the first action is the energy goes to promote the electron, and now there's 4 places for it to bond. But copper, it just always is that way already.
That slide, would you say that's like something you see on the test?
This slide?
The metal one.
Yeah, so far, this?
Yeah, yes.
Absolutely. You can see what you're going to see on the test.
Yeah. You even said it in the.
Right. I did. I even had it in the recording yesterday. Okay. First ionization. All right, we said that one. So the second one then is similar. It's between group 5 and 6A, and that's because the electron removed comes from a doubly occupied orbital. So we're saying it's a little easier to remove this one than it would to remove that one.
That's why they call it half bullets, so then they can take away the doubled up one.
Uh-huh. So, and that also comes from repulsion of other electrons in orbitals. So all these electrons are pushing each other a little bit away. So it turns out it's pretty much easier, even though it should be harder.
So is that something that like, I don't know, like we need to know the idea, but like it's not super major because it's just like within a certain orbital, right?
Yeah, it's not a major thing, but it's very commonly tested. Very commonly tested. And I don't know. That's the thing that bugs me about chemistry is it's true 90% of the time, but the test, they really like to test you on the 10% of when it isn't. And I don't know, that is kind of a pet peeve. All right, I think we're gonna wrap it up there. There's your summary. This will be your last slide. Where were we? All right, well, everything above here in the white that you can't see, that's what we had before. So this is the new addition. All right, I'm gonna end this. Oh, come on. So I can start.